Welcome, everybody. In today's session, I'd like to introduce to you one of our Amazon DynamoDB customers, DataXu. DataXu is based out of Boston. They develop and run the next generation marketing and analytics platform. Joining us today, we have Yakesa Kusuru and Rohit Delani from DataXu to talk about how they scaled their attribution system to handle billions of events per day. And my name is Padma Mallikarjunan. I am a technical account manager here at AWS. What to expect from today's session? I'll start with 15 minutes to lay out the overview of the benefits of NoSQL and DynamoDB, and then a high level of how DynamoDB integrates with other AWS services. That will help you start thinking about how you can apply this powerful service in your use case. And then I'll turn it over to our customer, DataXu, who is, of course, the main presenter today. To understand the benefits of NoSQL, let's start by looking at the differences between SQL and NoSQL and why. Because your choice of database technology will determine how your application scales. In a relational database system, the performance is generally tied to the hardware specifications of the primary server. And this is a technology that came 40 years ago. So to improve performance, you will optimize indexes and tables, but it is generally easiest to just move to a bigger box. You may create RAID replicas, but no matter the biggest and the fastest box you find out there, you will more or less run out of headroom. And you have to scale up or scale vertically using a relational database. NoSQL is different. NoSQL databases were designed to specifically overcome the scalability issues. So they scale out data to distributed clusters of low-cost hardware. Thereby, you get increased throughput while maintaining the low latency. Therefore, using NoSQL, businesses can scale virtually without any limit. So let's look at the differences from a schema design perspective. What you're looking at here is a generic product catalog where the table relationships are normalized. So a product can be a book. So there is a one-to-one relationship between a product table and the books table. So a book could be like the Harry Potter series Chamber of Secrets, right? Or a product could be an album. Or it can be a movie, say the Batman versus Superman movie, which has multiple actors. So you have Henry Cavill, you have Ben Affleck. Not shown here, but you need a separate table to store the actors' data. And these actors can be in many, many movies. So there is a many-to-many relationship between the movies and the actors' table. Now, imagine the type of queries that you will need to execute to say, show me all the movies starring an actor, or show me the entire product catalog. Now, that SQL is resource intensive. Notice also how you can run an ad hoc query to get data. So what it means is that relational databases are agnostic to access patterns, meaning they were not designed to be optimized for a specific access pattern. And businesses are starting to see these limitations with relational databases and switching to NoSQL. So how will you do this in NoSQL? Let's look at that example. You start by asking the question, how will my application access the data? So fast forward to today, compute is the costlier asset. So you need to optimize for that. So you will store the data in such a way that you can retrieve all of the information using just a select and not using any joins. So it will allow for duplication of data, storage, use hierarchical structures, and you're optimized for compute, and therefore it is very, very fast. So to put it all together, businesses are starting to see scalability problems with relational databases. I once had a customer who said that after they reached 3,000 requests per second, they had to move to a bigger box. But with NoSQL, you have a technology where you can scale to hundreds or even thousands of nodes, and the scalability bottleneck goes away. And they're great for OLTP applications at scale, where you need that real-time data access, and you want that fast performance. So that brings us to Amazon DynamoDB, the fully managed NoSQL offering from AWS. Fully managed. With just a few clicks, you will be able to create a table, specify any amounts of reads and writes, and DynamoDB will handle it for you. You don't have to launch or maintain any servers. You will get the fast, consistent, single-digit millisecond latency at any scale. It's highly scalable, so you can easily increase and decrease the throughput, and you only pay for what you use. And you have the flexibility to store document or key value data, and it integrates with Lambda. So you can trigger Lambda functions to execute based on events or changes in data in your DynamoDB table. And then, as in any business, you want to be able to specify the fine-grained access controls that specify who has access to what data. DynamoDB integrates with AWS Identity and Access Management and IAM to specify the user access. And here are just a few examples of customers who are using DynamoDB at a tremendous scale. Nexon, Supercell, powering their games using DynamoDB to provide a reliable, low-latency experience for millions of users. MLB, powering their IoT applications using DynamoDB. They can easily scale to support multiple games in a day or dial down to support just 1 or 2 games, and MLB only pays for what they use. Redfin, when you use their fully managed real estate app, and you browse through properties, it will show you the walk scores, the agent scores. All of the data is stored in DynamoDB for fast access. As a first-time home buyer myself, I found using Redfin made my home buying process really, really easy. Expedia says that using DynamoDB, they were up and running in less than a day, and there is no need for a team to maintain. So what do these customers want? They want to see fast, consistent, predictable, low latency at any scale, and DynamoDB was designed to deliver on that. So you can just focus on your application and not worry about the database. And this is the look at the console. You start using DynamoDB by creating a table. You specify a table name. You specify a partition key and an optional sort key, which will uniquely identify the items within the table. And then you can optionally specify the reads or writes, or you can accept the defaults, and then click Create. This table, which you just created with a few clicks, was highly scalable, highly durable, and it'll provide you that consistent, fast performance at any scale. So if you look at the APIs available in DynamoDB, the admin functions allow you to create, manage, and maintain a table. So you don't have to worry about creating read replicas or data partitions because it's a fully managed service, and all of that is taken care of for you. And of course, you have the CRUD operations to work with the items within a table, and you have the APIs for DynamoDB streams. And what are streams? You can think of them as a change log to capture the changes on your DynamoDB table. So every time an update comes into the table, they will start to appear on the streams in a time-ordered fashion. Streams have been around since 2014. It's widely used by our customers, and you can easily enable streams. They are highly durable, and the data in the streams is available for 24 hours. So what does that give you? You will be able to perform in-memory aggregations, let's say for a voting application that receives real-time votes, and you want to perform aggregations on that. And you can also use streams to easily integrate with other AWS services, and we will look at some of that. So as table updates start to come in, they will start to appear in the streams. And you can easily use an application that uses Amazon Kinesis Client Library, KCL-enabled application to read from the streams. And you can leverage the design patterns in KCL that simplifies stream processing. So what is a good use case for this? You have an application that's making data modifications to a DynamoDB table, and you can have a KCL application that reads this data and writes to a table in a different region. So now you have a replica that is in sync with the original, and just like that, you have enabled cross-region replication. DynamoDB Streams integrates with Lambda, so you can fire a Lambda function based on changes that appear on the streams. So what this function here is doing is Lambda is reading from the stream a data modification that tells us that Sinestro, who was a green lantern, just changed to a yellow lantern. And all this function does here is it prints that data out to the console, but you can take a lot of powerful actions based on using Lambda. For example, now you can use Lambda to read data from the streams, let's say an interesting JSON properties, and you can update a derivative table of DynamoDB and store that. Or you can update Elasticsearch, Cloud Search, or Elasticache. So you don't need to have a separate application that looks for data changes, and you can leverage Lambda to take care of that easily for you. Or you can use Lambda to send SNS notifications, and you can perform a variety of different functions. Now, Lambda, you can just upload code, and it will execute the code on your behalf. And it supports a variety of different languages. So if you like to write code, there are endless options what you can do with Lambda and DynamoDB streams. DynamoDB streams are great for real-time aggregations and analytics. Now, you can store any amount of data in a DynamoDB table. It can scale to petabytes. You can specify any amount of reads and any amount of writes. And you can use a KCL-enabled application to read from the streams and send it to various targets. Say, for example, you have you're looking at compliance verification data changes, and you can post those data to Redshift, which is our petabyte-scale data warehouse. I want to leave you with this reference architecture. This slide will be available to you to download after this session. So there are a variety of use cases that are enabled by DynamoDB streams. So you can read the streams data and keep your Amazon Elasticache updated for your caching application, or post update to Cloud Search or Elasticsearch, so you keep your search capabilities up to date. Or you can use EMR for further analytics and processing, or copy data to S3 and Amazon Redshift. So put together, think of these as different tools and building blocks that you can use to build your application. And I hope you can take away ideas to fit this into your use case. So with that, I will turn this over to Yakiza from DataXu to talk to us about their DynamoDB journey and share with us some of the best practices that they learned along the way.
Thank you, Padma. Good morning, everyone. Thanks for being here. Did you guys attend the keynote this morning? The snow oval was awesome. So I loved it. So I'm here to talk about the DynamoDB use case at DataXu. So here is what to expect from this session. A quick spiel on DataXu. We'll keep it short. And the use case in which we use DynamoDB, which is attribution. I'm going to touch on that one. Okay. And then why DynamoDB, right? What makes it what makes it align with our use case, and why did we go about, how did we go about choosing Dynamo, and what kind of what did we have prior to DynamoDB? So that's an important context to have. And then we'll look into the deployment architecture at a high level. Then my colleague, Rohit Dailani, is going to touch on the capacity performance and some lessons learned along the way. Good deal? Awesome. Let's go. All right, so who is DataXu? DataXu is a petabyte-scale marketing platform. We have spun out of MIT Labs, and here are the quick numbers. We operate at internet scale, and the numbers speak for themselves. What we do is we help the brands engage with the consumer along their journey. I'm going to talk about that, how exactly we do that in the upcoming slides. And our customer is an advertiser. So tactically speaking, we try to maximize the return on investment for our customers. Simply that. So our mission at DataXu is to apply data science to marketing problems. Quick run through the numbers. Our real-time engine, which I'm going to talk about, processes about 2 million transactions a second. This talk is about an hour in length. So during this time, our system would process about 7.2 billion transactions while I'm up here on the stage. So billions of impressions, clearly. petabytes of data, 180 terabytes collected on every single day. About 2 petabytes analyzed on a daily basis for our data science use cases. And then we, of course, the operations is, we operate out of 13 different data centers and regions. We are a hybrid model for now, but it's a 24/7 operations. All right, so real-time bidding. Very quick intro. I'm not going to go through the actual block diagram on this slide, but at a high level, what real-time bidding is let's say you are in the market to buy a car. You go to the internet, you go on the websites, you put in some parameters, you pull up some car, you do some side-by-side comparison of the cars, and then you might look for deals in your neighborhood. So as you're doing this, you are dropping hints and clues. But how does advertisers know how to connect with you? Because they might have deals in store. That's where we come in with our real-time capabilities. So real-time bidding is basically ads are auctioned off in real time using programmatic APIs. So we plug into that real-time auction platform. The real-time auctions are conducted through an ad exchange, and we participate in this on behalf of our advertisers. And when we bid on an ad slot, for example, so the ad slots are the ads that you see on the side of the page and the bottom of the page, we bid with a price, and the highest bidder wins. It's a second price auction, and the winner gets to serve the ad. So that's really real time. So one meta point that I want you to note from here is as real-time engine is serving these ads to the internet, it is generating lots of events. Let's just say billions of events, right? It says, hey, I served an ad, or I bidded on an ad, I didn't win. I bidded on an ad at this price, and I won. So it's collecting all these signals because it wants to learn from its behavior. And the system adjusts its real-time bidding strategies continuously. So that's the real meta point from this slide. So let's see how much we actually use DynamoDB, just to provide some context and some perspective. These are the production charts, both representing one table. On the left-hand side shows daily access pattern. On the right-hand side chart shows the hourly access pattern. We do have a little bit of a cyclical, as you can see in the hourly pattern. On the left-hand side chart, the y-axis, I don't know if you guys in the back can see it, even I can't see it, but it's really the billions of keys. So that's how much we access on a daily basis. And on the hourly chart, what you see is a little bit of a cyclical pattern, like I said. Again, just to give you some perspective of how much we use DynamoDB. So let's get into the use case in which we use this. OK, so what's attribution? Well, attribution is basically, some of you might already know this. In the world of marketing, attribution basically means allocating credits to the touch point that generated the desired outcome. The desired outcome might be, in this case, is an online purchase, right? When the ads are shown, let's say in this particular case, 2 ads were shown. User clicked after the second ad, and then they went to a website and made a purchase, right? So that's the sequence of events. These are 4 events, right? It's just it's just to keep things simple. Sometimes it's not 4, it could be 40, sometimes it could be 2. But the point of this pictorial is to give you a feel for what a customer journey or a consumer journey might look like. So there's 2 impressions, 1 click, and an online purchase. So why is attribution useful? Well, the marketers, the brands, they want to know insights to which marketing touch points are more profitable, so they can adjust their campaign spend accordingly to achieve best results for their business. And from our side, we also look at the same information because we know which impressions are generating positive signals, because we want to generate more conversions, right? That's how we get paid. So we also look at it. We also look at the same data to learn from it. All right. So the day in and day out, the system is collecting lots and lots of users, or lots and lots of events. I'm going to group them into two here. Each box represents one customer event chain, right? 2 impressions. This is a general schematic. 2 impressions, 1 event, and an activity in the first box. And 1 event, or 1 impression, 2 events, and followed by an activity in the second box. So attribution basically means in that user chain of events, or sequence of events, you find the activity or the conversion, and then you attribute to the impression that caused the conversion. In this case, it's called a linear attribution, where you take the value from that attribution and assign it equally to the impressions preceding it. This is called linear attribution. There are many other algorithms. I'm not going to bore you with the details here, but just to give you a feel. So the attribution engine's main purpose is to take all this data, sort it as the user time series data, find the activity, and then walk backwards. Make sense? There are 2 ways to do this, right? Again, I'm going to keep it grossly simple. There's, we can argue there's 1,000 ways to do this. But the 2 ways are, 1, you take all the data every single time and do a massive sort of the data, because we need the data to be sorted as time series by user by time series. So we can do a massive sort every single time we run the engine, or we can sort it and as the new events come in, we can insert them in the right place. So then it becomes a simpler compute problem. We opted the second, the latter. That's why we use DynamoDB. So why DynamoDB? Well, DynamoDB matches our use case really, really well. That's number 1. And I'll show you an example. And then it's a managed service, right? Padma talked about this in her slides. It's a fully managed service, and that's what we love about it. So prior to DynamoDB, we had a very popular key value store deployed in a colo. Lots of time was spent in maintaining that, whether it's the operating system upgrades or the software upgrades or rebalancing the data. Whatever it is, you spend a lot of time dealing with the maintenance issues. That was one. And also to rack it, and if you want to expand the capacity, you got to go through the normal process of ordering the machines, racking them, stacking them. It all takes time. Then you go to this funny rebalancing, which can take a long time and impacts your throughput and performance in real time. So we wanted to do away with all of those things. So we were looking for a managed service, and DynamoDB fits the bill. That's number 1. And there is never a need to over-provision, especially for ad tech, which is cyclical business. The November, December months are crazy, right? And then it goes up and down, right? It's cyclical. So there is no need to over-provision or provision ahead of time. And there's APIs for doing everything, whether it is creating the tables or expanding the tables or expanding the capacity or the throughput of the tables or ingesting the data into the tables. There's API for it. Fast and predictable performance is key, because the reason why you use a key value store is because of its performance. If it doesn't deliver consistent performance, it's no good. So this was one of our evaluation criteria when we made that switch. And we ran this at a scale of 5 requests per second. We ran this all the way up to 1 million requests per second. The performance was consistent, right? I'm going to pause there for a second, because when we were migrating our data, we accumulated this data for years, and we wanted to move all that data to Dynamo. And we were on a very strict timeline as we were moving this data. And then we called up Dynamo in the morning, and we said, hey, we need to bump up our capacity. How fast can we go? They said, how about 1 million requests per second? I said, are you kidding? No. They said, we can provision that for you. An hour later, we got the email saying, go for it. The system is provisioned. Now, this is like out of bounds, right? I mean, 1 million is not something we were even expecting. And Dynamo said, why don't you try it now? So we did it. And then it went 1 million and plus, super fast. We ingested the entire data in less than a day. The data that we've been collecting for over years has been ingested at this throughput in less than a day. So fast and consistent, we've tested this thoroughly, right? So it's fast and consistent performance. And the TCO, so TCO, the total cost of ownership dropped down to, the OpEx part dropped down to 0. We no longer have anyone on our staff to manage this system. It's a managed service. Why should we? But previously, with our previous key value store, we always had someone on the staff, on-call duties, and all the other good stuff that we have to deal with in running the system. So we no longer have this anymore. All right, let's look at the deployment very quickly. So this architecture is being transitioned out. Some of these MapReduce jobs are being replaced by Spark. If you guys want to understand why we are doing that, we are doing another talk on Spark. It's actually tomorrow at 4 o'clock if you guys want to come by. And here is on the left-hand side, you have Realtime Bidding Engine I talked about. It's generating lots of events. All the data ingestion happens through Kinesis for us. And then we have big 3 MapReduce jobs. The middle one is the attribution use case, which reads and writes out of S3. And that's the one that uses the DynamoDB. And that's where I'm going to focus for now. Oh, one thing I wanted to say. All these services are great, but the ecosystem of other services, such as CloudWatch and SNS and IAMs and VPC security groups, they're an important part of the fabric to deploy production use cases. So I just wanted to call that out. And you can see it clearly here. Even though the DynamoDB is the key cornerstone for our attribution use case, there's a bunch of other services that we use all around it. So let's see how the actual engine runs. First, we create an S3 bucket. We have data flowing from third parties and first parties. Then we have a data pipeline that runs EC2 machines, which then spins up EMR, which installs the applications as part of the bootstrap action. It does its checkpointing from RDS instance. As the application begins to run, it talks to DynamoDB. And then all the important events, the application metrics are recorded in CloudWatch. When thresholds are breached, SNS gets sent out to alert the engineers. And of course, we have a direct connect, so the system can reach back into the colo, and the developers can log into the system. Make sense? All right, so peeling the onion one more layer. Here is what we have. The Attribution Engine is inserting these events, again, the events in the order of billions, using APIs. And the event, they all flow into this table called user events. We have hash as the user ID, which is basically the partition key. And then we have range, which is the timestamp. And the payload is a binary compressed payload. I'll let Rohit talk about some of the details about how we structured this and in a little bit more detail. We have this table as a rolling monthly table. The reason for that is we wanted to avoid delete operations from this table. Delete operation counts as a write operation, and the write operation is obviously the most expensive operation. So what we do, and storage is cheap in Dynamo. It's not that much money. So we let the data accumulate. Our attribution look-back window is 30 days. So what we do is we accumulate the data for 2 months, 2 calendar months, and when we roll into the 3rd month, we drop the oldest partition. That's how it works. So we save on the delete operation. One of the comments that I get when I talk about DynamoDB, oh, DynamoDB is expensive. Well, it's not. You have to think about how the writes and the reads are counted. Once you know the math, we're going to explain to you the math in a little bit more detail. But once you know the math, you can manage your costs. So that's how we do it. We don't do the delete operations. We just let the table drop. And there's no fee for that. I mean, you can just simply drop it. All right, so we use, so there's in the, within the table, we maintain one-to-one relationship, right? The 4 events that I talked about in the attribution, this 2 impressions and followed by a click, followed by an activity, that's how it appears in the DynamoDB. So it's very easy to tell now, if we get the last event, which is an activity, we know where to insert. We know the user, we have the timestamp. We go in this table and insert it exactly where it belongs. And now the attribution is basically we walk backwards from that. So we pull all the 4 events for this user, and we do the attribution. It's a super lightweight compute because we've structured the data in the way it is to make it easy for us. And DynamoDB helps us structure that data, the time series data, to make it very easy for our use case. With that said, let me invite up my colleague, Rohit Dailani. He's going to talk us through the capacity, performance, and all the other nitty-gritty details. Thank you.
Thank you, Ekesa. Good morning, everybody. I'm Rohit. I work in the team which has built the Attribution Engine for DataXu, which uses DynamoDB at the center of it. So just a little show of hands. How many people are already working with DynamoDB in their system? Good, close to 40–50%. So I'll start with little basics so that everybody gets on the same page. And then we go deeper to understand things behind the scene. And you'll be able to appreciate some of these things here. So DynamoDB comes with the concept of a capacity unit, which is the measurement of throughput in DynamoDB. It's a little different from the other traditional systems which measure throughput only in terms of read and write operations. In DynamoDB, 1 read capacity unit is sufficient for doing 1 strongly consistent read per second for an item up to 4 KB in size. Now, if your item, which is a record also, is greater than 4 KB, and DynamoDB reads that, it's going to consume additional capacity units. Similarly, 1 write capacity unit is good for doing 1 KB item read per second. You also have to estimate the actual number of read and write operations which your application will perform on the table. This, along with the estimate item size, will help you determine the capacity units you would need to create or provision on your table. When a data is written to DynamoDB, it gets replicated into different availability zones within the region. And that's going to take time, but data will be eventually consistent. So DynamoDB supports different application read patterns, which are strongly consistent or eventually consistent. You, of course, have to pay double for strongly consistent read. Also, if you have local secondary indexes along with your table, and you write, it's going to consume additional write capacity units. To take a simple example, if you have an item which is 1 KB in size, and you write that, and that contains an index attribute, DynamoDB will consume 2 capacity units, 1 for writing to the table, and the 1 for writing to the index. Below a DynamoDB table are partitions. What is a partition? A partition is an allocation of storage, typically backed by the SSDs, and also replicated into different availability zones. A partition is sufficient for storing 10 GB of data, and also supports throughput requirements of 3,000 RCUs or 1,000 WCO. The number of partitions in a table would be determined based on the throughput requirement or the size requirement. There's a formula out there. So when you create the table, there is no storage. There is no data stored in that. And the number of partitions which DynamoDB will create for your table is based on the throughput requirements which you'll set. DynamoDB will create additional partitions in two reasons. If you store more data and the existing partition capacity is full, it will create more partitions behind the scene. Also, in case you provision your table with higher capacity settings, which is beyond what is the current provision capacity settings, DynamoDB will create more partitions. Now, partition management is completely done by DynamoDB. The application doesn't need to bother about it. And while the additional partition creation may be happening in the background, the table is available for throughout. Okay, so here are some examples to look at what we just discussed in the formula. Let's say we have a table which is 35 GB of storage and also provisioned with 1,000 RCUs and 500 WCUs. In this case, the formula gives us the number of partitions which is coming max from the size as 4. With this, the provision RCU, which is 1,000, is distributed equally into 4 partitions, and then each partition will support 250 reads per second and 125 writes per second. Imagine the same table grows up, and then we now have 1 TB of data in the same table, and you maintain the same provision capacities, but behind the scenes, the number of partitions have gone up, which is 100. So reads and writes per second will proportionally go down. What you see as a 5 and a 10 number is not really a low number. Just to put some things in perspective, VKS showed the events table which we have, which is 25 TB in size. That has 2,500 partitions for us. And we provision the table with tens of thousands of capacity units. So it'll be roughly around 20 read capacity units. So this number is no low. Third and fourth example, actually compare and contrast. So the table have the same storage, which is 100 GB, but they are different provision capacities. And you see the number of partitions between both of them are different, and so is the read and write capacity per partition. The meta point over here is sometimes your capacity requirements will dictate the number of partitions. Sometimes the storage requirements will dictate the number of partitions. Just to conclude, we have one more example, which is the table remains the same 100 GB. The provision capacities are 9,000 and 3,000. But let's say our data size is bigger than the average, what we spoke about as a 4 KB limit for a read capacity unit and 1 KB for a write capacity unit. So if we start storing data which is 5 KB, the item size is 5 KB in this case, DynamoDB will consume 2 read capacity units for reading this item and 5 write capacities for writing this item. And you would see the number of reads and writes per partition would be supported to a lower number. Just a small tip over here, the item size in DynamoDB is a sum of the attribute name as well as the value. So it'll help if you have your attribute names as smaller. Okay, so when the data is written to the DynamoDB, the hash key of the item is used to figure out which partition the data will go into. Now, in this example, we have a table with 10 partitions, what you see as like the beehives over there. And one of the partitions will be figured out based on the hash key where the data will go and write itself. We have the provision capacities of 9,000, 3,000 on this table, which gives 900 reads per second per partition and 300 writes per second per partition. So this is all the capacity is distributed equally amongst all the partitions. Each partition will work within its quota. There's no sharing between the partitions for the capacities. You can hit each of these partitions with up to 900 reads and 300 writes per partition before you start hitting the limit of the partition, after which all the requests within the time period will start throttling. So this is a very common question in forums. My partitions, I don't know. My provision capacity, I know. And my consume capacity, I know, which is all apparent from the DynamoDB charts. And my provision capacity is somewhere here. My consume capacity is here. So I'm throttling still. Why does that happen? You go to Stack Overflow, Amazon Forums, Quora, very common question. I'm sure everybody in the room will now be able to answer that. So the point over here is you may be still well within the provision capacity at the global level on the table, but individual partitions may start throttling you. We'll talk about some of those things in detail, the hotkeys, for example. Okay, so let's say you have created a table, provision capacity, start writing to it, and you may hit throttling, or you may not hit throttling. How do you know? These are CloudWatch charts from DynamoDB, which measure the throttling. In this case, you can see both our read and write requests are getting throttled. You may be able to tie these to the CloudWatch alarms and get alerted and take action. Additionally, all your requests from the application will also start getting the provision throughput exceeded exceptions at this point. So one of the challenges with DynamoDB is to get the right scale. By that I mean the throughput capacity settings which suit your pocket as well as your user's need. And we all have been spoiled by ease of removing the costly resources like the ASGs with the EC2s, the EMR with the auto scale. It would be great if DynamoDB had something like this out of the box. It doesn't, sorry. But it's not very difficult to build one. We did something in our system. The principle is very simple. JKS said everything is possible through the API in DynamoDB. So you can adjust the provision capacity settings using the API with a little bit of code, which can respond to the consumed capacities. We built our auto-predictive scaling, which looks at the past usage data in the table, and we also anticipate how much of data is coming, and we scale up and down the table to the expected throughput which we would need from the table in the coming cycle. What you can see over here is this provision capacity in the red bars and the consume capacity in the blue bars. So we scale up and down, and we pay only for what we use. Couple of things to watch out if you are doing something like this. You would pay for the provision capacity even if you're not consuming it. So you may want to look at the reserved capacities, which is cheaper than the provision on-demand capacities. Also, when you increase the capacity to a higher level, DynamoDB may create additional partitions. But when you bring it down, it doesn't remove the partitions. So your throughput per partition may be going to be on a different scale. There are a couple of companies out there which are working on solutions like what we are showing up here. And I believe they also have some machine learning models to learn about what is being used in the past and adjust accordingly. DynamoScale, Fitted Cloud. And there is a dynamic DynamoDB solution also out there as a CloudFormation template, which can automate all this for you. So coming to some tips and lessons learned while working with DynamoDB for the last 1 year and so. Understand the scaling. So when you create the table the first time, you should provision the capacities to your 12-month peak. This way, the DynamoDB will ensure you have created enough partitions so that you are kind of supported for your peak period. Understand the hotkeys and throttling. This can happen if you have a pattern wherein a popular item is getting read. And such a case can be solved by putting a caching layer in front of it. Padma touched upon how you can use the DynamoDB streams, and you can invalidate the caches from there. DynamoDB also has a lot of application metrics. They're all in the CloudWatch. But we also did a couple of our own stuff, things like empty reads. In DynamoDB, if you do a read which comes back with no data, that's empty read, that still costs you capacity. So you start counting them. We also started putting some application metrics around the data sizes, and that's going to help. And we put them back into the CloudWatch so we can compare and contrast along with the DynamoDB metrics, and you can probably understand your application's usage patterns from there. Configure the table alarms on capacities. If you're hitting throttling, it's no use. So you need to know if you are going to hit throttling. So capacities allow you to basically put an alarm on percentage, and then you can notify yourself and take action. Build your application with tolerance for outliers. So outliers are rare in a well-designed system. We have been running with DynamoDB for over a year now. We've seen very few outliers, but be aware of them. There are application patterns to solve that. Cut off the request if it's going beyond a threshold, something of that order. AWS SDK already provides a retry with backoff. When the throttling is happening, this can be retried, and then let's say the subsequent second, the throttling doesn't come in. So you can still go ahead and perform the request again because it's a retriable request. So DynamoDB, AWS SDK already does that. If you're using the low-level API, you should build something yourself on this. There's a lot of best practices you should go look at, which are documented by Amazon before you're designing your tables. They are super helpful. AWS has also documented their service limits. You should look at your application requirements and try to look against that. So how do you reduce the read and write capacity units? The first one is not kind of related, but the batch API in DynamoDB is super. And it helps you do the operations in parallel. It kind of gives you the flexibility of a thread pool without putting the complexity in the code. You can use the batch get API to read up to 100 items in a single request. You can also use the batch write API to put or delete 25 items in a single request. Thing to watch out over here would be the requests in parallel or requests in a single would still consume the same capacity. So don't get fooled by that. We saw our the events table in which we store the data against the user. So there's a primary key, which is the user ID, the hash key, and there's a range key, which is the timestamp. And then we store the event data. So we optimize a bit more from there. We started packaging. All our events were like smaller than 1 KB. So we grouped multiple events for a user within a time frame and put it into a single record. This helped us reduce the number of writes and reads which we had to do. We also compress the data, of course. Use the LZ4 compression, which is very similar to LZO, but has a very fast decompression speed. And this is all simple to do because the object mapper in the Java SDK was super efficient. You could override that, and the application doesn't need to do anything. So we kind of built a small SDK over the AWS SDK, and the application it works with a similar way. How do we handle the deletes? We don't do deletes. We talked about the rotation table earlier. We build the tables on a monthly basis, always write to the current month table, and when we read, we go back to the previous tables. And at the end of the attribution retention window, which is like 30 days, the look back, we go and drop the table. No code for delete, no cost for delete. Understand scaling. Scaling takes a lot of time, especially when you are scaling to a big number of capacity and a large number of partitions. We saw that when we are building our predictive scaling. So we do it well in advance so that the table is prepped up. It's going to take a couple of seconds to a couple of minutes. Some debugging tips from our lessons and learnings while operating the system in the production. Log to the application logging. That's your only place wherein you'll go understand what's happening in the production. Log application matrix. I told you about a couple of application matrix which we log along with the DynamoDB matrix. TCP dumps. I don't think you will need to go over there, but let's say if there are network glitches, you can take TCP dumps, analyze them using the Wireshark. One of the key findings we found over there is we use DynamoDB from within EMR. So we are never out of the AWS data center. And we figured out it's faster to use HTTP instead of HTTPS without any reason, so we switched that. And that's very easy to switch off using the client configuration utilities, and it's just a flag change. AWS SDK also logs a request ID. It doesn't log, it provides a request ID, which you can log into your system, in your application, but it also comes with a verbose logging. This is helpful if you are trying to debug your issue with AWS support. So request ID is a thread which binds your application to the backend of DynamoDB. So you can track in the flow of the request using the request ID. We dynamically enable the request ID logging when we hit some thresholds. CloudWatch, super useful. Use it for everything, and then we also have alarms on that. One of the less publicized feature of DynamoDB is that local DynamoDB. We have used it for all our unit testing and integration testing. It also comes with an interactive web shell, which you can use to play with the DynamoDB API within your local environment. You don't have to even go out of your box. With that, I'm going to leave you with one last thought. Is DynamoDB good only for high-scale applications? I would say no. You can start small, and DynamoDB offers seamless scaling, and then you can upsize, downsize your capacities based on your need. If you need a fast, predictable performance at any scale, DynamoDB may be a good choice for you. In fact, in our attribution system, we have migrated all our tables into DynamoDB, irrespective of the scale they operate at. With this, I'm done. These are our email IDs you can reach us on, and we'll be taking questions now. Don't forget to complete your evaluations.